Hello everyone. As we have gone through the concept of ideal gas, what is ideal gas, what are experimental or ideal gas equation of state, kinetic theory of gas, which is used to explain the experimental gas laws, which was applicable only for ideal gases. Now, while starting with this ideal gas, we have mentioned that all the gas which is existing in this universe are known as non-ideal gas or a real gas, because these gases does not follow the ideal gas equation strictly at all temperatures and pressures. So these gases are known as a real gas. So these gases shows deviation from ideal behavior. Now the question is, why these gases or this real gas shows deviation from ideal behavior? Now, while discussing ideal gas, we have explained or we have used the term these real gases shows ideal property only when the pressure is very low and the temperature is very high. So for those gases, if pressure is very low and temperature is very high, at that condition only all these real gases approaches to that of ideal behavior. But the question is, why there is a deviation from ideality? Now the answer for this question lies in the postulates that we have assumed in kinetic theory of gas. So while mentioning the kinetic theory of gas, there I have given you some star mark. There are two important postulates of this kinetic theory of gas, which says the volume occupied by the molecules of gas is negligible or approximately zero in comparison to the volume of the gas. Second postulate was that whenever these gas molecules are moving, then there is no force of attraction or repulsion between the gas molecules. That is, the motion of a particular gas molecule is independent of its neighboring gas molecules. So these two conditions are responsible for deviation of these real gases from ideal behavior. Now let's see why this shows deviation from ideality. Now we all know that gases can be easily liquefied. More or less every gas can be liquefied. We increase the pressure and temperature is decreased, then these gas can be liquefied. The best example is LPG, the liquefied petroleum gas that we use for cooking. So inside this cylinder we have a gas which is in liquid form. That means gases can be liquefied. So if the gases can be liquefied, then there must be some attractive force between the gas molecules. So there is an attractive force between the gas molecule. This attractive force was completely ignored in ideal condition. So when we assume the ideal behavior, we have assumed that there is no attractive force between the gas molecules, but in reality, since the gases can be liquefied, there is an attractive force between the gas molecules. The second point is, since the gases can be liquefied, this liquid will have certain volume. If the liquefied gas has got certain volume, that means the volume of the gas must also be there. So there must be some finite volume of the individual gas molecules. Otherwise, how can this liquefied gas can have certain volume? If the liquefied gas has got certain volume, this indicates the individual gas molecules do have certain volume, though it may be very extremely small, but these molecules do have certain volume. So this was again completely ignored in ideal gas. That was completely ignored in kinetic theory of gas. So there we have mentioned the volume occupied by the molecules of gas is negligible to the total volume of the gas. But the reality says these molecules do have certain volume which was completely ignored. Since the gases can be liquefied, in between the gas molecules there must be some attractive force which was again ignored in case of ideal behavior. So the cause of deviation is there is an attractive force within the gas molecule which was completely ignored. Second, the individual gas molecules do have certain volume which was again ignored in case of ideal gas. So this was the reason why real gases shows deviation from ideal behavior. So the heading is real gas. So if someone says what is real gas, means all those naturally existing gas are known as real gas because these does not follow ideal gas equation. So these real gases approach ideal behavior only under restricted conditions. So real gas tends to ideal gas. For this, the condition is pressure is very low and temperature is very high. So only under this restricted condition real gases shows ideal behavior. Now the question is, why a real gas shows deviation from ideality? So the answer is, why is real gas shows deviation from ideality? So the answer is, real gas has attractive force between the gas molecules, and the real gas do have certain volume. Gas molecules do have certain volume. So these two conditions was completely ignored. Now these two is coming from because gas can be liquefied. So since the gas can be liquefied, there must be some attractive force as well as the molecules must have certain volume. So these two as postulates was the main cause for deviation from ideal behavior. So the question is, we have to modify the ideal gas equation including the attractive force as well as the volume factor. So therefore look at this. Pressure correction, because of this attractive force, suppose we have a gas molecule, these gas molecules which is just about to strike, ये just strike करने वाले हैं. अब जब ये मॉलिक्यूल यहाँ पे स्ट्राइक करेंगे तब भी क्या बनेगा, प्रेशर डेवलप होगा. अब जब ये मॉलिक्यूल यहाँ पे स्ट्राइक करने वाला होगा, इसके पीछे वी हैव अ सर्टेन गैस मॉलिक्यूल्स होगा. अब ये गैस मॉलिक्यूल और इनके बीच में देयर इज एन अट्रैक्टिव फोर्स. सो बिकॉज ऑफ दिस द पीछे वाला गैस मॉलिक्यूल इसको पुल करेंगे. जब पीछे वाला गैस मॉलिक्यूल इसको पुल करेंगे, द मोमेंटम with which these gas molecules will strike this container, क्या होगा, मोमेंटम कम होगा. अगर मोमेंटम कम होगा तो फोर्स पर यूनिट एरिया क्या होगा, कम होगा. If force per unit area is less, then the pressure will be less. That means because of this attractive force, जब ये मॉलिक्यूल जब स्ट्राइक करने वाला था, इसके पीछे वाला मॉलिक्यूल इसको खींच लेगा. जब ये पीछे की तरफ खींच लेगा तो ये जब जिस फोर्स के साथ स्ट्राइक करने वाला था वो फोर्स कम हो जाएगा. अगर ये फोर्स कम हुआ तो फोर्स पर यूनिट एरिया, जिसको हम लोग डिफाइन करते हैं प्रेशर, तो प्रेशर क्या होगा, कम होगा. तो इस प्रेशर को मुझे करेक्शन करना है बाय यूजिंग द कंसेप्ट ऑफ एट्रैक्टिव फोर्स. तो therefore look at this pressure PI means ideal pressure is equals to the actual pressure, जिसको हम लोग कहते हैं real pressure, plus some P prime. So PI is ideal pressure, PR is real pressure, and this P prime, this is pressure lost due to attractive force. तो ये पीछे जो ड्रैगिंग फोर्स है उसकी वजह से कितना प्रेशर लॉस हुआ, अगर उसको ऐड करेंगे देन रियल प्रेशर जो करा था प्लस प्रेशर लॉस ड्यू टू दिस अट्रैक्टिव फोर्स, अगर इसको कंबाइन करेंगे देन दिस गिव्स यू द आइडियल प्रेशर. तो इफ यू लुक एट दिस, अगर इस इक्वेशन को देखा जाए देन आइडियल प्रेशर इज ऑलवेज ग्रेटर देन द रियल प्रेशर. So therefore look at this. Now we have to define this P prime, pressure loss due to attractive force. This pressure loss P prime due to attractive force is directly proportional to N by V square, where this N is number of moles of gas, V is the volume of gas. So therefore this N by V, this represents concentration. That means the concentration of gas molecules जो just यहाँ पे स्ट्राइक करने वाला था, अगर ये ज्यादा मॉलिक्यूल यहाँ पे स्ट्राइक करने वाला होगा तो पीछे भी ज्यादा मॉलिक्यूल ट्रैक कर रहा होगा, तो concentration ज्यादा होगा तो प्रेशर लॉस भी ज्यादा होगा. So removing this, we can look at this. P prime is equals to some constant A, N square divided by V square, where this A is known as attractive force. Van der Waals constant is a Van der Waals constant which represents attractive force. So that means if the van der Waals constant A, अगर ये attractive force ज्यादा है तो pressure loss will be more. अगर ये attractive force कम है then pressure loss will also be less. So अगर ये attractive force ज्यादा है that means the gas molecules can be easily liquefied. तो अगर हम लोग कहते हैं कोई भी गैस मॉलिक्यूल आसानी से लिक्विफाई कर सकते हैं, so if I say a gas can be easily liquefied, that means for those gas the value of A which represents attractive force, that is a van der Waals constant which represents attractive force, should be high. तो ज्यादा ए का वैल्यू ज्यादा होने से एट्रैक्टिव फोर्स ज्यादा होगा, अगर एट्रैक्टिव फोर्स ज्यादा होगा तो ईज ऑफ लिक्विफिकेशन ज्यादा होगा. सो दिस इज P prime, pressure loss due to attractive force. तो therefore इसको यहां पे यूज किया जाए, देन प्रेशर आइडियल इज इक्वल्स टू प्रेशर रियल प्लस पी प्राइम इज ए एन स्क्वायर अपॉन वी स्क्वायर। इफ यू लुक एट दिस, अगर इससे ध्यान से देखा जाए तो आइडियल प्रेशर इज ऑलवेज ग्रेटर देन रियल प्रेशर। ये मेरा प्रेशर का करेक्शन हुआ। नाउ यहां पे एक था हमने ए, वी हैव टू डिफाइन ये वाला ए, तो इसका क्या यूनिट होगा, लेट्स डिफाइन। इफ यू लुक एट दिस यूनिट ए एन स्क्वायर अपॉन वी स्क्वायर ये प्रेशर के बराबर है, तो यूनिट ऑफ दिस ए एन स्क्वायर बाय वी स्क्वायर शुड बी इक्वल्स टू यूनिट ऑफ प्रेशर। सो देयरफॉर लुक एट दिस, A is equals to P V square upon N square. P, that is pressure. Pressure standard unit is Pascal. Volume standard unit is meter cube. So meter cube square meter-6 divided by N square, that is mole square. So this is the unit of van der Waals constant A, which represents attractive force. So this is A. Now अभी मैंने आपको बताया ना, the characteristics of A क्या है, larger the value of A, the more easily the gas can be liquefied. अगर A वैल्यू ज्यादा है तो gas can be easily compressed. So अगर different गैसेस है दैट ए वैल्यूज आर गिवन है, अगर आपसे क्वेश्चन पूछ दे कि व्हिच ऑफ द फॉलोइंग गैस कैन बी मोस्ट इजीली लिक्विफाइड, सो द गैस विद लार्जर वैल्यू ऑफ ए कैन बी मोस्ट इजीली लिक्विफाइड। जैसे जैसे ए वैल्यू बढ़ते जाएंगे, ईज ऑफ लिक्विफिकेशन ऑफ गैसेस क्या होगा, इंक्रीज करते जाएंगे। तो ये ए का यूनिट हुआ और ये ए का कैरेक्टरिस्टिक्स है। देन सेकेंड इज साइज करेक्शन, वॉल्यूम और मॉलिक्यूलर साइज करेक्शन। तो अगेन यहां पे लोग हमने कहा कि भाई इंडिविजुअल गैस मॉलिक्यूल्स का सर्टेन वॉल्यूम्स है। अगर ये सपोज इंडिविजुअल गैस मॉलिक्यूल्स का वॉल्यूम है, तो सपोज इस कंटेनर में मान लेता हूं कि 1 मोल गैसेस है, तो इस 1 मोल गैसेस का कुछ फाइनाइट वॉल्यूम होगा। सो अगर ये टोटल कंटेनर का वॉल्यूम है, उस वॉल्यूम में से सर्टेन वॉल्यूम, ये वाला वॉल्यूम गैस मॉलिक्यूल्स ने ऑक्यूपाई किया, तो द रिमेनिंग वॉल्यूम सिर्फ इस रिमेनिंग वॉल्यूम है, दैट इज नोन एज फ्री वॉल्यूम। अब इस वॉल्यूम में गैस मॉलिक्यूल फ्रीली मूव कर सकते हैं, बिकॉज दिस पोर्शन ऑफ द वॉल्यूम क्या हुआ, गैस मॉलिक्यूल्स ने ऑक्यूपाई किया, तो यहाँ पे मॉलिक्यूल्स का मूवमेंट रेस्ट्रिक्टेड है। सो दिस इज व्हाट वी कॉल एज द वॉल्यूम और साइज करेक्शन। तो ये तभी पॉसिबल है इफ इंडिविजुअल गैस मॉलिक्यूल्स का सम फाइनाइट वॉल्यूम्स है। अगर ये वॉल्यूम नहीं रहता तो करेक्शन करने का जरूरत ही नहीं है। सो देयरफॉर लुक एट दिस, V ideal is equals to V real means the actual volume of gas, इसको हमने कंसिडर किया, माइनस NB. So this is the volume of container which was we assume to be the volume of gas, but in reality क्या है, इस कंटेनर का वॉल्यूम जिसको हमने गैस का वॉल्यूम माना था, उससे सम वॉल्यूम गैस मॉलिक्यूल्स ने ऑक्यूपाई किया। तो ये B, this B is nothing but the volume occupied by 1 mole of gas, while N is the number of moles of gas, and numerically this value is equals to 4 times the volume occupied by volume occupied by 1 mole of gas is equal to 4 times volume occupied by a gas molecule. So therefore look at this, this is 4, volume occupied by single molecule is 4 by 3 pi r cube, where r is assumed to be the size of individual gas molecule. Now this is for 1 mole, so we have to apply this by Avogadro number. So numerically this B, which is the volume occupied by 1 mole of gas, equals to 4 times volume occupied by gas molecules. This B is also known as co-volume or excluded volume. Why this is known as co-volume or excluded volume? The reason being, total volume में से इस वॉल्यूम में गैस मॉलिक्यूल फ्रीली मूव नहीं कर सकती, बिकॉज इस पार्ट ऑफ द मॉलिक्यूल वॉल्यूम में गैसेस मॉलिक्यूल ने ऑक्यूपाई किया है, तो ई पार्ट ऑफ द वॉल्यूम में मूवमेंट ऑफ गैस मॉलिक्यूल इज रेस्ट्रिक्टेड, एक्सक्लूडेड है, बाकी रिमेनिंग पोर्शन है इसमें गैस मॉलिक्यूल मूव कर सकते हैं. सो दिस इज द वॉल्यूम और मॉलिक्यूलर साइज करेक्शन. एंड दिस बी, look at this, ये आपके पास n minus b है, so this must be equals to the unit of volume. So therefore look at this, nb must be equals to volume, unit of volume. So unit of volume is meter cube, so therefore b is equals to meter cube divided by n, that is mole, volume per mole, standard unit. So again look at this, अगर the size of gas molecule अगर ज्यादा है तो compressibility कम होगा. अगर गैस मॉलिक्यूल का साइज कम है तो गैस मॉलिक्यूल कैन बी इजीली compressed. तो अगर आपसे क्वेश्चन पूछते हैं कि भाई डिफरेंट गैसेस हैं जिसका सपोज ए वैल्यू सेम है, बी वैल्यूज डिफरेंट है, विच वन इज मोर कंप्रेसिबल, तो जिसका बी वैल्यू ज्यादा होगा कंप्रेसिबिलिटी कम होगा, जिसका बी वैल्यू कम होगा दैट इज मोर कंप्रेसिबल. सिमिलरली अगर बी का वैल्यू कांस्टेंट है, ए वैल्यू डिफरेंट है, तो जिस गैस का ए वैल्यू ज्यादा होगा एट्रैक्टिव फोर्स ज्यादा होगा, कैन बी इजीली कंप्रेस्ड. तो ये है आपके पास बी, एंड दिस B represents, this is again van der Waals constant van der Waals constant, which represents molecular size. So A and B, these are the van der Waals constant which represents the attractive force and the molecular size. So after this volume correction, the ideal gas equation can be modified. And अगर before this यहाँ पे देखिए, so ideal volume is always less than a real volume, whereas ideal pressure is always greater than the real pressure. So after this pressure correction and volume correction, we should be getting an equation which is applicable to the real gases. So अगर ये P prime and B factor अगर remove कर दिया जाए, then again we are having ideal gas equation. But since there is attractive force and molecular size, so this has to be modified. तो चलिए इसको रिमूव कर देते हैं. So we have looked at this ideal gas equations. So Pi Vi is equals to nRT. So Pi is equals to P plus An square upon V square. Vi is V minus Nb is equals to nRT. So this equation is a well-known equation which is known as real gas equation or van der Waals equation. A real gas equation or van der Waals equation, because this equation is applicable, this equation is applicable for real gases. But for 1 mole of gas, means N is equals to 1, this equation can be written as P plus A by B square N minus B is equals to R. This is for 1 mole of gas, this is for n mole of gas. So this is what they call as a real gas equation, which was defined by van der Waals in terms of this constant attractive force A. In honor of this scientists, this equation was named as van der Waals equation. So this is a real gas equation. So I have told you why ideal gas shows deviation, because of this volume factor and attractive force. So once we this modify, then we are developing an equation which is applicable to the real gas. So this is the real gas equation. A and B are the van der Waals constant. Now we have to memorize the characteristics of this A and B, as I have given you, as I told you what are the characteristics of this A and B. So this is the real gas equation. Now we have defined why there is a deviation. Now this deviation of real gas from ideality is expressed by a factor known as Z, which is known as compressibility factor. So this Z, which is known as compressibility factor, is defined as the ratio of observed molar volume to that of ideal molar volume. This is observed molar volume, this is ideal molar volume, means volume occupied by 1 mole of ideal gas under standard condition, STP condition. So look at this, the ratio of observed molar volume by ideal molar volume, this ratio is defined as compressibility factor Z. Now this compressibility factor versus P diagram. So we have a graph. This is E. Z equals to 1, this is for ideal case. This is for hydrogen, helium, so this is Z versus P graph for different types of gas, real gas. For all ideal gas, Z versus P graph is 1. For ideal case, this compressibility factor Z is always equals to 1. But for real gas, this is greater than 1 for hydrogen and helium, but less than 1 for some case, and at some pressure again this increases 1. Now we have to explain why this variation of graph. First of all, look at this. This Z is equals to Vm divided by Vim. Now we have look at this. Pv is equals to nRT. So therefore look at this. For ideal case, V by N is equals to RT by P. So this V by N, that is Vim. So this is equals to RT by P. So therefore for ideal case, so we have Vm divided by RT by P, or this is PVm divided by RT. Now this molar volume, that is volume divided by N, so this can be written as PV divided by nRT. So for ideal case, PV is equals to nRT, so therefore Z is always equals to 1 for ideal gas. For ideal gas, this compressibility factor Z is always 1. This is independent of pressure and temperature. But for real gas, this Z is a factor depends on temperature as well as pressure. So this is greater than 1, less than 1, or at some temperature this is greater than 1. So for ideal gas, this Z is greater than or less than 1. Maybe greater than 1, maybe less than 1 for some gases. Now we have to explain this. Why this Z factor is greater than 1 for some gas, why this is less than 1 for some gas. So for this now we will take the help of this van der Waals equation. By use of this van der Waals equation we will explain this variation of Z. So for the real gas, this Z is a factor of temperature and pressure. Means this is a function of temperature and pressure. For all real gas, Z value depends on temperature as well as pressure, but for this real ideal gas, Z is independent of the pressure. Means for all pressure, Z is always equals to 1. Now we'll take the help of van der Waals equation to explain this graph. So let's explain this graph. So for this, I'll keep this graph as it is and I'll rub this part. So first we'll explain for this hydrogen. For hydrogen and helium, value of A, that is van der Waals constant A, which represents intermolecular attractive force, is extremely negligible. So this is the reason why hydrogen gas and helium gas cannot be liquefied easily. So it's very difficult to liquefy hydrogen and helium. So when we say hydrogen and helium is very difficult to liquefy, that means the value of E is extremely small. If E is extremely small, so we can say E is approximately equals to 0. So therefore, from van der Waals equation we get P plus A by B square, means for 1 mole, V minus B is equals to RT, N equals to 1. So since A is equals to 0, so we can say P this is 0. So V minus B is equals to RT. So we say PV minus PB is equals to RT. So divide this equation by RT, we get, so get this PV by RT is equals to RT by RT plus PV by RT. So this PV by RT, this was defined as compressibility factor Z. So this is equals to 1 plus PV by RT. So look at this, Z is 1 plus something, pressure cannot be negative. This is size factor cannot be negative. R and T, this cannot be negative. So the only factor is, so this is 1 plus some factor. So therefore, that is Z is always greater than 1 for hydrogen and helium. So if someone asks you why Z is always greater than 1 for hydrogen and helium, the reason being, for hydrogen and helium, the A value, that is the van der Waals constant A, which represents the intermolecular attractive force, is extremely negligible, and this is approximately 0. So from this condition we are developing this, Z is always greater than 1 for hydrogen and helium. Now coming to other gases other than this hydrogen and helium, at low pressure condition Z is less than 1. At some intermediate pressure Z equals to 1. At very high pressure Z is greater than 1. So we have to explain this low pressure condition and high pressure condition. So we'll use this equation. So first thing, at low pressure condition. At low pressure condition. Now look at this, pressure is low. If pressure is low, volume should be high. So pressure is low. So if pressure is low, volume should be high. If volume is high, then this V minus B will be approximately equals to V, because the molecular size factor B is very small. So very large volume minus a very small quantity is approximately equals to V. So we take this approximation. Pressure being low, volume should be high. If volume is high, then this V minus B or this van der Waals constant B can be ignored or neglected. Means approximation says V minus B is approximately equals to V. So therefore again, from van der Waals equation we have P plus A by V square into V, because V minus B is approximately equals to V. So we say this is equals to RT, because N is equals to 1 for 1 mole of a gas we are considering. So simplification gives PV plus A by V is equals to RT, or we can say, look at this, PV is equals to RT minus A by V. Now divide this equation by RT, so we get PV by RT is equals to 1 minus A by RTV. So PV by RT, this is defined as Z, which is equals to 1 minus A by RTV. Now if you look at this, Z is 1 minus something, so this is always less than 1. So this Z is less than 1. So at low pressure condition, Z is always less than 1. The reason is, at low pressure condition, volume being high, the molecular size can be ignored. So under this condition, the nature of gas depends on this A. As the value of A increases, that is, as the attractive force between the gas molecules increases, the value of Z decreases. So the depth in the graph, look at this, the depth in the Z versus P graph, this represents the value of A. As the depth is more, means the value of A will be more. So the gas having larger value of A will be having more depth, means that gas can be more easily liquefied. So at this low pressure condition, nature of gas depends on A factor. So low pressure, Z is less than 1, gas depends on A factor. Now coming to high pressure condition, at high pressure condition, so pressure being high, so we have pressure is high, volume must be low. So if volume is low, then B cannot be ignored, because already volume is low. This is again small value, so this becomes as significant. So since pressure being high, we can ignore the value of A. A can be ignored, that is P plus A by V square will be approximately equals to P. So A is being small, B being, so this A by V square will be a very small compared to that of P, so we can ignore the value of A. So under this condition, from van der Waals equation, again we have P, V minus P is equals to RT for 1 mole of the gas. So therefore this gives you PV is equals to RT plus PV. Dividing this equation by RT, we get PV by RT is equals to 1 plus PV by RT. So PV by RT, that is defined as Z, so V is equals to 1 plus P into B divided by RT. So if you look at this, Z is always greater than 1. So at high pressure condition, the nature of gas depends on this B. So low pressure, A factor decides the nature of gas. At high pressure condition, B factor decides the nature of gas. So at this high pressure, nature of gas depends on B factor. So for this gas, a real gas other than this hydrogen and helium, so at low pressure condition, A factor dominates. As the A factor dominates, there is a decrease in the value of Z as the value of A increases. Now at high pressure condition, the nature of gas is dominated by the factor B. As the factor B dominates, the value of Z is always greater than 1, so slope becomes positive. Before this, slope is negative. So low pressure, A dominates, high pressure, B dominates. At some intermediate, the vector A and B factor cancels out. At that point, the value of Z equals to 1, that is, it approaches ideal value. So this is how we define deviation from ideality. But for a given gas, if temperature changes, then how this graph changes for the same gas at different temperatures. Suppose this is Z, this is P, this is Z equals to 1. So we say this is ideal case. Now suppose we have a real case. This real case, so this is suppose temperature T1. This is a temperature T2, temperature T3, temperature T4, temperature T5. Now look at this. Moving from T1 to T5, the depth in the graph decreases. This is for same gas at different temperatures. So as the temperature changes from T1 to T5, the depth in the graph decreases, and the graph at this particular point T5 runs almost parallel to that of the ideal gas equation. So moving from T1 to T5, temperature will increase, that is T1 is less than T2, less than T3, less than T4, less than T5. That means for the given gas, as the temperature is increased, the gas will tends to the ideal behavior that we have explained and used earlier. So this particular temperature T5, look at this temperature T5. At this temperature T5, the Z versus P graph runs almost parallel to that of ideal gas. So this T5, when the nature of gas changes to ideal, this temperature is known as boil temperature. So boil temperature TB. Now this boil temperature, why this is known as boil temperature? Because at this temperature Boyle's law is applicable. That means the gas shows ideal behavior. So this temperature is known as boil temperature because at this temperature Boyle's law is applicable. So as this point Boyle's law applicable means ideal behavior. So as the temperature increases, the gas changing from real to ideal behavior. So at very high temperature, the gas will show definitely ideal behavior. So this is what we are saying, boil temperature. So as the temperature increases at a certain temperature, when the Z versus P graph is almost parallel to that of ideal gas, that particular temperature is known as boil temperature. Why? Because at this temperature Boyle's law is applicable, means the gas shows ideal behavior. That means at this point A factor and B factor will be approximately 0. So we have ideal. So mathematically this boil temperature is A by RB, where A and B is a van der Waals constant. Van der Waals constants A and B. So for any given gas, if van der Waals constant A and B is given to it, then we can easily define what is the boil temperature, means at which the gas will show ideal behavior. So it is A by RB. So just from calculation point of view, we require this. So boil temperature is temperature at which Boyle's law is applicable. Mathematically this is equals to A by RB, where A and B is the van der Waals constant. So this is how we define the deviation of the real gas from ideality. And to define this, we take the help of a factor which is known as compressibility factor Z. So as I have shown you, for some gas the value of Z is always greater than 1. For some gases at low pressure the value is less than 1. At a high pressure this is greater than 1. Again, we have shown you high pressure condition, low pressure condition, but an extremely low pressure condition. Extremely low pressure condition, all these graphs are processed to that of ideal value. So at extremely low pressure, the gas shows ideal behavior. At very high temperature condition, I can look at this graph runs parallel to that of ideal behavior. So extremely low pressure condition and high temperature condition, all real gases will tend to show ideal behavior. So this is the concept of real gas. So hopefully we enjoy this class and we discuss more about this derivation from real gas